Am I audible to all of you? Hello?
Yes, sir.
Okay, so the course is almost over, and today it will be the last class, okay? So the numericals that we had done in the class, I will send all the numericals in the group. So you please collect it from your CR and all, okay? So for your clearance, can you see my screen?
Yes, sir.
Okay.
Degrees of freedom is the one of the most
So
important
this is
concepts
on the degrees of freedom. Just try to understand.
in kinematics, which means how many variables are required to determine position of a mechanism in space. Position of this 4-bar mechanism could be determined just by knowing angle or position of one of the member. So degree of freedom is 1. Similarly, degree of freedom of this cam and follower mechanism is also 1. But to determine position of this slider crank mechanism, we should know angle or displacement of at least 2 members. So here degrees of freedom is 2. In this video we will learn how to predict degrees of freedom of a mechanism. Consider this rigid body in space. It could have 3 translatory motions like this. Also it could have 3 rotary motions like this. In total we need 6 inputs to determine its position. So, degree of freedom of rigid body in space is 6. If the body is in a plane, it can have only 3 motions. 2 translational and 1 rotational. So degree of freedom of a rigid body in a plane is 3. Now, consider this planar mechanism. A mechanism is a collection of rigid bodies, or links, connected through pairs, provided one link is grounded. If this system were not connected like this, then each link, except the ground, would have 3 degrees of freedom. So total degrees of freedom, or mobility, is 3 into n minus 1. N represents total number of links, in this case 3. But when we connect it together, through pairs, links will not have the same 3 degrees of freedom. If joint between 2 links is having surface contact, like this joint, then both the links will have same translatory motion in x and y directions. So, for each such pairs, there will be a deduction of 2 mobility from the total, where LP represents number of pairs with surface contacts. Such pairs are called lower pairs. In this case we have 2 lower pairs. Now consider this joint, which is having a line contact. If joint between 2 links is having line or point contact, both the links should have same translational motion along the common normal. However, it could have different motion in tangential direction. So, for each such pairs, there will be deduction of 1 mobility from the total. This kind of pair is called higher pair. Here we have got 1 higher pair. So this mechanism has got 1 degree of freedom. Means, by knowing position of only 1 can, we can completely determine this mechanism. So this is the equation to find out degree of freedom of a planar mechanism, known as Koothbach Equation. Back to same old planar mechanisms. This mechanism is having 4 links and 3 lower pairs. So mobility is 1. Cam and follower is having 3 links, 2 lower pairs, and 1 higher pair. So mobility is again 1. This mechanism is having 5 links and 5 lower pairs. So mobility is 2. If the mechanism is 3-dimensional in nature, you could easily derive an equation for mobility using the same concept. The main thing here will be determination of nature of pair. To know about velocity analysis of a mechanism, check next video. Thank you.
We are going to study the dynamic behavior of the simplest form of structural system, which is the single degree freedom system. As the definition suggests, this system can move in only one direction, such as the car shown in the figure, which can move only back and forth. In particular, this lecture focuses on free vibration, which is initiated by inducing an initial displacement and an initial velocity to the system, and then letting it free to vibrate without any external force acting on it. Through the use of this simplified single degree of freedom system, we are going to show how the equation of motion is formed. We are going to study the free vibration of undamped systems in which no energy dissipation takes place. Subsequently, we are going to study the free vibration of damped systems in which energy is being dissipated, resulting in a decaying motion. two types of damping are examined. Viscous damping, in which the damping force is proportional to the velocity, and Coulomb damping, in which the damping force is constant. Well, so the solution to the equation of motion is derived analytically. By the term solution to the equation of motion, we mean the evaluation of the response of the system at any time instant during its vibration.
Please mute your mic. Please mute your mic. Someone please ask him to mute his mic.
Expressed as displacement, velocity, or as any other response quantity. An essential aspect in structural dynamics is the energy input in the system and the energy dissipation, which will also be examined. An appendix is also included with a review of a simplified version of the matrix structural analysis method. Using this method, the stiffness of simple structures can be calculated, which is then used to form the equation of motion. We now present some examples of single degree of freedom systems. One such system is a car that is fixed on a base which moves only back and forth. Another system is a single-story portal frame whose mass is assumed to be concentrated at its top and is allowed to deform only in the longitudinal direction. A third system is a cantilever whose mass is assumed to be concentrated at its free end and is allowed to deform only in the vertical direction. The formulation we are going to present in this lecture can be used with all these systems. Let's examine the car, which is an example of a single degree of freedom system. The car has certain properties, such as a mass, denoted as m, that is assumed to be located at its center. It is fixed on a base through a spring that has a certain stiffness, denoted as K. A viscous damper is also introduced between the car and the base to account for the energy dissipation during the motion of the car. The damper has a certain damping coefficient, denoted as C, the meaning of which we are going to study later in this lecture. The position of equilibrium of the car is the position at which the elongation of the spring is 0. The difference between the position of the car and the position of equilibrium is called the displacement, denoted as U. In this course, we sometimes use the term deformation interchangeably with the term displacement, for reasons that we are going to explain later when we examine earthquake excitation. Because in the field of structural dynamics, we are studying the response of the system with respect to time, the displacement is expressed as a function of time. In order to form the equation of motion, we first draw a free body diagram on which we mark the forces acting on the car when it is in motion. Shown in the diagram in white arrows are the displacement, the velocity, and the acceleration, and in black arrows, the forces. There are two types of forces: the internal forces and the external forces. The first internal force is the stiffness force, denoted as Fs, which is caused by the elongation of the spring and is equal to the product of the stiffness constant K times the displacement U. This force has an opposite direction to the displacement. The second internal force is the damping force, denoted as Fd, which is caused by the motion of the system and is equal to the product of the damping constant C times the velocity U dot. This force has an opposite direction to the velocity. The velocity is denoted here as U dot and is the derivative of the displacement with respect to time. In this case, and in most of this lecture, the term damping refers to viscous damping. The third internal force is the inertia force, denoted as Fi, which is equal to the product of the mass m times the acceleration U double dot. This force has an opposite direction to the acceleration. The acceleration is denoted here as U double dot and is the derivative of the velocity with respect to time. In the case of free vibration, the external force is zero. We are now going to examine how the equation of motion is formed for the case of free vibration. In the first of the two approaches, the equation of motion is formed using Newton's second law of motion. Newton's second law of motion states that the resultant force acting on a body is equal to the body mass times the acceleration. We form an equation which contains the summation of the forces acting on the mass on the left hand side and the mass times the acceleration on the right hand side. We then restructure the equation by moving all internal forces to the left hand side and the external force, which is zero in the present case, to the right hand side. The resulting equation is the equation of motion. In the second approach, we use the Lambert's principle of dynamic equilibrium, which assumes an inertia force and states that the internal and external forces acting on the body are in equilibrium when the body is in motion. Therefore, we sum up all internal forces on the left-hand side of the equation and the external force, which is zero in the present case, on the right-hand side. The resulting equation is the equation of motion. We can see that both approaches result in the same equation of motion.
Now count the degrees of freedom a rigid body has. Let us say that our body looks like this. Okay, it is a three-dimensional object. It's rigid, meaning the distance between different points in the body let's say this is some point and there's another point in the body, the distance remains fixed with time. Okay, that cannot change. Let's say the distance between these 2 points is, for example, A. Clearly, there are no true rigid bodies in the universe. I mean, these distances will change, but if you are not interested in the details of very finer details, many bodies can be considered to be rigid. Okay. Let's see how many degrees of freedom this one has. So what we really are asking is, how many numbers should be specified to tell uniquely where the object is and how it is oriented, right? Meaning where each particle of this body is located. Okay. Once you specify this, you have specified everything, and the total numbers you need to make that specification is the degrees of freedom. Okay. Now let's take this point first. Now if this point is really located here in space, in bringing it, in specifying that it is here, you use up 3 numbers. And those 3 numbers are the x, y, and z coordinates of this particle. So you have used up 3 numbers in bringing it here. Okay, that's good. Now let's look at this particle, some distance a away. Given this being fixed here, this one, what all freedom this one has? Now clearly, this guy can be, if only this point number 1 is fixed, this has a lot of freedom. This could be here, or this could be anywhere on a sphere of radius A. So imagine a sphere of radius A with the center at point 1. Okay. And if you are only fixing this point, the point number 2 could be anywhere on the sphere, right? Now if you say, okay, the point number 2 is somewhere, it is specified, then in making the specification you need 2 numbers. Okay. So if you want to say, okay, the guy is somewhere here or here or here, you have to tell the theta and phi. Okay. Because as we saw in the previous video, specifying a point on a sphere requires 2 degrees of freedom. Okay. So once we have said, okay, the guy is here, I have used up 2 degrees of freedom now. Okay. So let's say these 2 are here. Is the rigid body which you have here is uniquely fixed in space? Well, no, not really. Look at this point. Let's say take point 3. So what we are asking is, if I have told particle number 1 is here, if I have told particle number 2 is here, does it mean that everything is fixed? All other particles are fixed at their locations? No. Why? For example, this particle number 3 could be here or could be anywhere on a circle about this axis. So you could clearly rotate this entire body about this as an axis. Okay? That you could do. And if you do that rotation, your point 1 will be still here, your point 2 will still be here, but all the other points apart from the ones on the axis will change their position, right? Because we are going to rotate it like this. So clearly, the entire body is not still fixed in its location in space by just telling this and this. So let's fix this one. How many numbers you need to fix point number 3? Well, you need only 1 number. Why? Because this has a free. And once you tell the angle which it makes with some reference point and some reference axis, let's call it again theta prime. So if I specify one angle, the point number 3 will also be fixed in space. Okay. Okay. Now, is there anything else left? Once you have said this guy is here, this guy is here, and this guy is here, can a fourth particle be somewhere else other than being here? Well, there is no freedom left now. You know that once any of these three, all the 3 points which we have taken here, 1, 2, 3, once they are fixed, there's nothing you can do to change the positions of other particles. It's all rigidly fixed now because the distances are all fixed. And from this counting, you clearly see that you have a total of 3 plus 2, 3 plus 2 plus 1, 6 degrees of freedom. Okay, so in general, let me write down, next page maybe. No, it doesn't. So in general, a rigid body has 6 degrees of freedom. Okay, but there may be special cases where the degrees of freedom may be lesser than this. For example, if you have, let's say, a rod, okay, one-dimensional rod, then how many degrees of freedom it will have? Okay, let's take any 2 points on this. This guy, as before, has 3 degrees of freedom. To bring it here, you need to specify x, y, and z coordinates of this. Then this, let's call it point 1. This one will be called point 1. Now, point number 2 could be anywhere on the sphere which is centered about 1, right? Just like before. So you can think of a sphere about point 1. Okay, it's not looking very nice. I will not draw. So just imagine a sphere of radius a, where a is the distance between 1 and 2. Imagine a sphere, and the point 2 could be anywhere on the sphere if you just specify x, y, and z. And to specify where the point 2 is on that sphere, you need 2 more numbers, theta and phi, as before. And once you have specified point number 2 using theta and phi, there is nothing else to be specified, right? Because all the other points get fixed in space. So this particular special case has 3 from here, 2 from here, so 3 plus 2 equals 5, 5 degrees of freedom. Okay, that's good, and maybe later I will talk about more about rigid body motion and
So, so what I will do is I will send the numericals in your class group, and you people please collect it from your CR. Okay, CR, please take the responsibility of circulating it to everyone. Okay, that's it. So there is terrible network issues today.